Quantum uncertainty dictates 100% of reality at the smallest scales. A 2022 University of Vienna study confirmed this with 99.9% statistical certainty. But your own brain uses quantum uncertainty to make split-second decisions right now. Werner Heisenberg stared at a blackboard in Copenhagen. In June of 1925, the 23-year-old had invented matrix mechanics. By 1927, Heisenberg was ready to publish the radical consequence of his own equations. The uncertainty principle: the more precisely you measure where something is, the less you can know how fast it is moving. It is not the observer effect, where the act of measurement disturbs the system. It is a fundamental, inescapable property. The mathematical expression is deceptively simple. Delta x multiplied by delta p is always greater than or equal to half of the reduced Planck constant. That constant, Planck's constant, valued at 6.626 times 10 to the negative 34 joule-seconds. It is tiny, almost unimaginably small, but it is not zero. And because it is not zero, Heisenberg realized that the operators for position and momentum simply do not commute. In classical physics, you can measure a car's speed and its location at the same moment with perfect accuracy. A planet has a definite position and a definite momentum simultaneously. The act of defining one property forces the other into a haze of probability. The implications were devastating to the old deterministic worldview. If you cannot know both position and momentum, Laplace's demon, the imaginary creature that could know the position and velocity of every atom and therefore predict all future events, Edwin C. Kimball would point out in 1937 that the uncertainty principle presumes particles have properties like position and momentum in the first place. Rudolf Haag later noted that position in quantum mechanics is not an intrinsic property of a particle at all, but an attribute of an interaction between the particle and a detector. It is a sign that our classical language has reached its breaking point. The uncertainty principle does not merely prevent us from knowing the world. The uncertainty principle is not a wall that blocks our vision. It is the engine that builds the world. Classical physics would tell you that nothing exists there. But the energy-time form of the uncertainty principle allows for a temporary violation of energy conservation, provided it happens quickly enough. And so, everywhere in the universe, even in the deepest void between galaxies, pairs of virtual particles blink into existence and annihilate each other in a flicker of borrowed time. It is a seething foam of quantum activity, constantly creating and destroying. It is measurable. In 1948, the Dutch physicist Hendrik Casimir predicted that two uncharged metal plates placed extremely close together in a vacuum. The reason is that the vacuum between the plates has less room for virtual particles than the vacuum outside. In 1996, Stephen Lamoureux at the University of Washington measured the Casimir force with remarkable precision. But the principle does more than generate ghostly particles. In 1911, Ernest Rutherford had shown that the atom is mostly empty space, a tiny, dense nucleus surrounded by orbiting electrons. Atoms should not exist. The uncertainty principle saves them. If an electron were confined to the nucleus, the uncertainty principle demands that its momentum would then be enormous, so large that the electron would have enough energy to escape. The electron is forced into a compromise. The atom is stable because the electron is uncertain of where it is. Niels Bohr understood this intuitively. His 1913 model of the atom, with electrons confined to discrete energy levels, was a brilliant guess at a deeper truth. The electron cannot have zero energy, even at absolute zero. The principle demands a minimum energy. Nothing in the universe is ever truly still, even at the bottom of a quantum well. This brings us to the deepest implication. The uncertainty principle is not a statement about our ignorance. It is a statement about the nature of reality itself. The universe does not have a hidden ledger where exact positions and momenta are recorded. The properties do not exist until an interaction forces them to be defined. This is the heart of the Copenhagen interpretation. The electron does not have a position until it hits the detector. It exists as a wave of possibility, spread across space. Albert Einstein could not accept this. In a 1926 letter to Max Born. But an inner voice tells me that it is not yet the real thing. The theory yields a lot. I, at any rate, am convinced that he does not play dice. Einstein believed there was a deeper reality beneath the quantum fuzziness. But the experiments have not been kind to Einstein's intuition. In 1964, in 1982, Alain Aspect's experiments in Paris showed that the universe violates Bell's inequalities. The uncertainty principle is not a veil hiding a classical reality. It is the fundamental law of the quantum world. The fuzziness is all there is. And that is when the real scientific puzzle emerged. If reality is fundamentally uncertain, what is the nature of time itself? The energy-time uncertainty principle does not just allow virtual particles to flicker in and out of the vacuum. It opens a door to something far stranger, the possibility that the uncertainty in time itself might allow the future to influence the past. It is a direct mathematical consequence of the equations, and it has been tested in laboratories. Consider the quantum eraser experiment. In a standard double-slit experiment, a particle passes through two slits and creates an interference pattern on a screen, proving its wave-like nature. The act of knowing destroys the wave behavior. After the particle has passed through the slits and been detected, you can choose to erase the information about which path it took, and the interference pattern reappears. The decision to erase or not erase is made in the future, but it determines the pattern that appeared in the past. John Wheeler, the great American physicist who coined the term black hole, Wheeler imagined a photon from a distant quasar, its path bent by the gravity of an intervening galaxy. On Earth, billions of years later, an astronomer could choose to measure which path the photon took, or to recombine the paths and observe interference. Wheeler called this participatory universe, the idea that observers are not passive witnesses but active participants in the creation of reality. In 2007, physicists at the University of Vienna led by Anton Zeilinger, the results confirmed Wheeler's prediction. The future decision determined the past behavior. The universe does not have a fixed history until it is measured. This is where the uncertainty principle reveals its deepest philosophical sting. If the past is not fixed until observed, the arrow of time, which we experience as the relentless march from past to future, may be an emergent property of quantum decoherence, the gradual loss of quantum information as systems interact with their environment. In his 2017 book, The Order of Time, he describes a universe where the equations of physics work perfectly well without a time variable. The uncertainty principle, then, is not a cage. It is the mechanism by which the universe gives itself room to breathe. Without uncertainty, every particle would have a predetermined trajectory stretching from the Big Bang to the heat death of the universe. The fuzziness at the quantum scale is what allows atoms to form, molecules to bond, and chemistry to happen. It is the crack in the deterministic clockwork that lets consciousness slip through. Heisenberg himself understood this. In his 1958 book Physics and Philosophy, he wrote that the uncertainty principle forces us to abandon the objective description of nature. There is no world out there independent of our observation. The world is a web of relationships. The physicist John Archibald Wheeler put it even more starkly. No phenomenon is a real phenomenon until it is an observed phenomenon. So when you look at the night sky, remember that every photon that enters your eye has traveled across the universe, its path uncertain until the moment it strikes your retina. The universe is not a stage upon which the drama of life unfolds. And the uncertainty principle is the scriptwriter, leaving every line open to revision until the final curtain. They suggest that the universe does not have a single history, it has every possible history, and our observation selects one. This is the many worlds interpretation. Everett proposed that every quantum measurement splits the universe into branches, each realizing one possible outcome. In another, it went right. The uncertainty principle, in this view, is not a limit on knowledge, but a description of the branching structure of reality itself. Niels Bohr dismissed it as not even wrong. The physics establishment largely ignored him. He left academia and worked as a defense analyst for the Pentagon. It was only decades later, after his death in 1982 from a heart attack at the age of 51, that his interpretation gained serious traction. Today, many cosmologists working on quantum gravity and the multiverse consider Everett's framework, but the uncertainty principle does not just shape the large-scale structure of reality. Consider the proton, the heart of every atomic nucleus. In 1968, deep inelastic scattering experiments at the Stanford Linear Accelerator Center. They are composite objects, made of three quarks bound together by the strong nuclear force. The force is carried by particles called gluons. The uncertainty principle dictates that these gluons cannot be confined to a single location. They smear out into a cloud of virtual particles that constantly flicker in and out of existence. The mass of the proton, the very stuff of ordinary matter, is not primarily the mass of the quarks themselves. You are not made of solid stuff. You are made of frozen energy. The principle also governs the behavior of black holes, the most extreme objects in the universe. In 1974, Stephen Hawking applied quantum field theory to the event horizon of a black hole. The energy-time uncertainty principle allows pairs of virtual particles to be created near the horizon. But at the event horizon, one particle can fall into the black hole, while the other escapes into space. The black hole loses mass. It evaporates slowly. Hawking radiation, as it is now called, means that black holes are not eternal. A black hole the mass of the Sun would take about 10 to the 67 years to evaporate completely. The uncertainty principle, operating at the boundary between quantum mechanics and gravity, this brings us to the deepest unresolved tension in modern physics. The uncertainty principle works perfectly in the regime of quantum mechanics. General relativity works perfectly in the regime of large masses, where quantum effects are negligible. The equations break down. You cannot describe the singularity without a theory of quantum gravity. String theory, loop quantum gravity, and other approaches attempt to unify these frameworks, but none has been experimentally confirmed. The uncertainty principle may need to be modified at the Planck scale. And that is where the human story returns. Werner Heisenberg, the man who formulated the principle in 1927. He was not a cold mathematician. He was a deeply reflective man who loved music. In his 1958 Gifford Lectures at the University of St. Andrews, published as Physics and Philosophy, the observer and the observed are entangled. Heisenberg believed that this lesson extended beyond physics into the realm of human knowledge itself, that every act of understanding is a creative act. In 2026, quantum computing companies like IBM and Google use the uncertainty principle to manage qubit initialization and error rates. It is not an obstacle to be overcome. It is the foundation upon which quantum advantage is built. The very feature that makes quantum computing powerful is the same feature that limits classical measurement. So the next time you find yourself unable to decide between two paths, the universe itself cannot decide until it is forced to. Every quantum particle exists in a haze of possibility, waiting for an interaction to crystallize its reality. The fuzziness is not a flaw. It is the source of all structure. Without it, the universe would be a frozen clockwork, ticking through a predetermined eternity. The only question that remains, the one that keeps physicists awake at 3 in the morning, is whether the story has an author or whether the pen is writing itself. That vacuum, as we have seen, is not empty. It is a roiling sea of virtual particles. But what if that sea is not just a passive backdrop? What if the vacuum itself contains a hidden structure? In 1975, Stephen Hawking and George Ellis published a paper that hinted at something extraordinary. The extreme gravitational field warps the vacuum, creating a polarization effect. Virtual particle pairs are not created randomly. The uncertainty principle, operating in a gravitational field, becomes a lens that focuses quantum fluctuations into specific patterns. It means that the vacuum carries information about the geometry of the universe. In 1998, the physicist Gerard Hooft proposed that the uncertainty principle might be the key to understanding the holographic principle. The uncertainty principle sets a fundamental limit on how much information can be packed into a given region. If you try to cram too much information into a small space, the universe, in this view, is a hologram. The three-dimensional world we experience is a projection of a two-dimensional surface at the cosmic horizon. Leonard Susskind, the Stanford physicist who had debated Hawking about black holes, seized on Hooft's idea. In 1995, Susskind published a paper titled The World as a Hologram. He showed that the uncertainty principle, combined with the Bekenstein-Hawking entropy formula for black holes, it is a pixelated screen, where each pixel has a size set by the Planck length. This brings us to the most recent experimental test of the uncertainty principle's reach. In 2012, a team of physicists at the University of Vienna led by Marcus Arndt They fired a beam of C60 molecules, known as Buckyballs, through a double slit. It is a large, complex molecule, far larger than the electrons and photons that usually demonstrate quantum effects. The uncertainty principle applied to them as well. The wave nature of matter does not disappear at larger scales. It simply becomes harder to observe. The experiment confirmed that the uncertainty principle is not limited to the subatomic realm. It governs all matter, from quarks to molecules. The reason we do not see quantum effects in everyday life is not that they are absent, it is that they are washed out by decoherence. The constant interaction with the environment, the jostling of air molecules, the thermal vibrations of atoms, all conspire to destroy the delicate quantum coherence that would allow us to observe the wave nature of a baseball. The deepest mystery remains. The uncertainty principle tells us that the universe is fundamentally probabilistic. But probability is a mathematical concept, not a physical thing. In 1952, David Bohm proposed a hidden variable theory that restored determinism by introducing a quantum potential that guides particles along definite trajectories. But it does so by positing a non-local force that acts instantly across space. Einstein called it spooky action at a distance. The uncertainty principle, then, is not just a law of physics. It tells us that the universe is not a machine with hidden gears. It is a living system of relationships. The physicist John Archibald Wheeler once said that the universe is not a collection of things. It is a collection of acts. It is the mark of a universe that is still being written, moment by moment, observation by observation. And the question that keeps physicists awake at 3 in the morning